website. Can you read it actually? Is it too low on the screen?
Yeah.
Whether you can see it or not. But I did check it, it does work. So if you're interested, this contains some quite old papers on block waves and on band structure in periodic media. And they predate the whole photonic crystal, photonic band gap field. And there's also a review paper on that website, which you can just simply download. So they're all available there. Not many people know that in 1975, a German professor in Hamburg called Raman actually started a student on a PhD project to basically make photonic crystals and explore the propagation of light in two-dimensional periodic structures and wavebands, and did a lot of beautiful experiments way back in 1975. And it finished in 1980, which is 15 years before the whole field of photonic crystals became fashionable, so you might be interested in that. Okay, so this information will be available on the file that you can download later on, I hope, on the web. So just to summarize, where's my pointer gone? It was a pointer, but it's disappeared. Okay. So yesterday I took you through the history of fabrication and some basic aspects of the photonic crystal fibers. And then I talked about the fibers in which this classification number, this delta n infinity, the difference in refractive index between the core and the cladding, is positive at long wavelengths or at very low frequency. Today I'm going to talk about the other kind of fiber where the delta n infinity is less than 0. So this is the more unusual structure, because if your core refractive index is less than the cladding index, then the conventional total internal reflection mechanism of course doesn't work. So you have to use a photonic bandgap kind of mechanism to trap the light. So I'm going to talk about this. So let me get started on this. What happened? Weird. What happened there? Maybe I touched the wrong key. Okay. So if we go back to, this is back in 1998, to the first report of a fiber which guided by a photonic bandgap effect. This is a picture of it, and this is work that was done by my postdoc Jonathan Knight. You'll see this is a very simple experiment. We take, maybe I'll just use the mouse. So here on the left you see the experiment. We made this fiber. We drew it out. We took it out of the drawing tower. Took a short length of it, about 25 millimeters long. We put it in a simple microscope and have a lamp down below, a white light source, focus it in, look through the microscope, and immediately you can see whether or not the fiber is doing anything interesting, whether it guides light, what interesting effects there may be that you can see. It's a very simple experiment, and you compare that with some of the very difficult experiments that people do on photonic crystals. This is so simple you wouldn't believe it, very easy. So it was very exciting for us to see this beautiful pattern in the fiber core. This is actually a fiber where the holes are arranged in carbon rings. So these are the hollow regions, and in the center here, you have a closer look. We're putting in white light, and the white light is guided pretty well in these silica regions with the holes in between in the cladding. But in the core, we can see that blue light has been specially selected from all the different wavelengths going in, and is guided in the core in a beautiful it's got 6 petals. It's like a flower. It's very, very, very beautiful picture, I think. So what is going on here? Well, if I just now show you what the structure looks like, this is the structure that we made. These are very large areas of glass. These are hollow regions which are filled with air, and in the center of the structure there's an additional hollow channel. And of course this means that the average refractive index, if you average the refractive index in this region, it will be lower than the refractive index out here because of the extra hole. So it's delta n infinity, which is negative in this case. The scale, this is about 3 microns. So this is the structure. You'll see there are some very tiny holes here. These are simply because of the fabrication process. These are leftover interstitial holes that didn't quite collapse. They're also very small, as you may see. So, okay, let's now just mark out the different regions. These yellow circles represent these large areas of glass, and the white dotted lines represent the air, the hollow regions, and so this is the core hole and so on. So keep that in mind, and let's go back to the picture you saw before. And now you can see that the blue light is choosing to sit in, it's actually sitting in the glass. The light is not actually in the hollow regions in this case. It's certainly present in the core, but in quite a complex mode shape. What's interesting of course, to ask here is why on earth doesn't the light sitting in these silica regions, why doesn't it just leak away into these large areas of glass? So if you think about the number of guided states, the number of photonic states in these large areas of glass, you would think this is very odd, you know, why doesn't the light just leak away into this and disappear from the core? And of course, this brings us to another way of thinking about how these structures work. If you think about these blue kind of dots as modes of the structure, they will have a very specific value of beta, that wave vector component parallel to the axis. So they have a very sharply defined value of beta, and it just so happens that in this case, that value of beta is not phase matched to any of the modes that could guide in these large glass regions. So the light is unable to couple to anything, so it stays in the core. And that's a kind of a way of looking at how these fibers work. So it was a very exciting result for us back in '98. This was the first time anyone had ever done this, and to see something so beautiful was very nice. But of course, that was not the real goal of the work. I mean, the main goal of this negative delta N work was to make a hollow core fiber in which the light was actually trapped in a hollow core, or trapped in empty space. So I kind of call this section the hollow core challenge. You know, I mean, if we went back, let's say 15 years, and you talked to someone and said, I'm going to give you a challenge, I want to have a very low loss hollow core single mode fiber, how would you do it? Is it possible? I think most people would say it was impossible. So here's the question: how can we keep light tightly focused in vacuum over long distances in a single mode? So we don't want to just, you know, you could maybe come up with various possibilities for solving this question. So let's have a look at them. Well, one simple thing is you may say, okay, why don't I just use a lens, focus the light down. Here's the laser beam coming in, we focus it down, we keep the light tightly focused, very tightly focused. But of course, as you all know, there's a depth of focus associated with this, which Lord Rayleigh wrote about 100 years ago. Although you can get a high intensity, the distance over which you can keep high intensity is relatively short. So you could maybe try a stronger lens, and of course you get a tighter focus, but the depth of focus gets even smaller. In fact, it doesn't really help to use a lens. You can throw the lens away, and you get this. You get the same product of spot size and depth of focus. It turns out in this situation, that's not a solution clearly. You could do something else. You could think about, well, let's take a capillary, make a very small hole in it, and coat it with metal. So here we are, there's the metal. And you could think, well, this is obviously a nice way. Metal reflects light very well. This should work. Then you have a closer look at this. Of course, you all know, particularly those of you who work in metamaterials, that compared to dielectrics, metals absorb very strongly at optical frequencies. That's not a good idea. And so if you make the bore, that's to say the diameter of the tube is the bore of the tube, if you make that smaller, and it needs to be very small for the structure to be single mode, you'd like it to be single mode, then the overlap between the light that's in here and the metal increases, so the absorption gets bigger and bigger and bigger, and at the end of all this you can very easily discover that the losses are many orders of magnitude higher than in the silica glass itself. So this is not a solution, except for very short propagation distances for a single mode structure. You could be more imaginative, and this is an idea that came out of MIT, although the original idea for such structures dates back to a Russian group in the 1960s, and then Amnon Yariv worked on it in the early 1970s. It's what's called a Bragg fiber. It's a series of concentric rings. And you have to use pretty exotic materials in order to be able to make a fiber like this. And what these people used was a combination of chalcogenide glass, that's an infrared glass, which melts at relatively low temperature if you choose the right one, and polymer. Now, you may, if you know anything about these materials, they have certainly polymers have very high absorption at infrared wavelengths, and chalcogenide is not the best material in the world, so in fact you're using materials that have extremely high intrinsic absorption for light, but nevertheless the structure can work because this brag structure, this cylindrical stop band that this produces, is able to keep the light from penetrating into the materials. So the light stays in the hollow region and is strongly rejected from these very lossy materials. So the overlap between the light and the lossy material is very small, and as a result you can get reasonably low loss. 1 dB per meter is the figure that these people have demonstrated at a wavelength of 10 micrometers. That's a carbon dioxide laser wavelength. And in fact, there's a company that's come out of this work called Anomaly, I think is the name of the company, and they're using these fibers in surgery for the eye. So the surgeons love it. It's a flexible tube that can deliver 10 micron radiation to the eye. So that there are some nice applications, but the loss is really very, very high compared to what you'd like. You'd like that to be 0.01 dB per meter, especially if you want to use this carbon dioxide laser light to cut materials. You want to cut metals or whatever. You want hundreds of kilowatts of power, and obviously you don't want a lot of loss in the fiber because it would melt at these enormously high powers. Okay, this sort of structure has not really been successful for communications wavelengths. Another thing you might try, and is just to forget about your knowledge of physics and say, okay, well, let's to hell with this. Let's just take a capillary with a hollow tube. We focus light into it, and maybe the light will go far enough along the tube so that we could put some gas in here and get some interactions, and maybe that would be okay. It turns out, well, of course, the hollow capillary is an anti-guide. It leaks. Clearly, because the refractive index is the wrong way around, and there's no photonic band gap to keep the light in, so you get quite strong leakage. But if you operate at say a wavelength of 800 nanometers, high sapphire laser, and the diameter of this hollow tube is of order 100 micrometers, then the attenuation is not too bad. You can get 1 meter of interaction before the light falls to 1/e of its initial intensity. So it's not too bad. But that's not a single mode hollow structure. We want single mode. To get single mode, you need to be down around 10 micrometers, and then the loss, the leakage rate increases about 8,000 times, so it's totally impractical. You would never use a hollow capillary for single mode waveguide. Because this is where the hollow core PCF really steps in and completely changes the scene in this case. Now we can keep light tightly trapped in a hollow core over very long distances. So we can kind of effectively go back to the Rayleigh thing and say to Lord Rayleigh, okay, fine, but we have a way of keeping light tightly trapped in vacuum. And that's the really important thing here. You can keep light tightly trapped in a conventional fiber core over hundreds of kilometers. That's the way they work. But that's in a solid material. Here we can keep light tightly trapped in a hollow, in vacuum essentially, over kilometer distances, as it turns out. So it really is quite a revolutionary result for many applications. So let me take you back to this diagram I showed you yesterday. This time we're going to be taking the triangular lattice and have a hollow core in the center. Same parameters as before. Theta, you remember what that is, I think. And here's the diagram you've seen before. Of course, you get a different diagram depending on the structure, but this is just to illustrate what's going on. Previously, we looked at guided modes in this region, so in the solid core version of the PCF, but now we're going to be operating in one of these band gaps, and in fact, to get guidance in a hollow core, you have to operate at a point like this, and this is a point where the cladding material has a full two-dimensional photonic band gap, so there are no photonic states within this range of beta values and this range of frequencies. But the light is nevertheless allowed to propagate in vacuum because we're on the left-hand side here of the vacuum line. So this means that the light can form a resonant state in the core because the light is free to propagate in vacuum, but it's unable to penetrate into the solid material around it. So we have the perfect conditions for making a waveguide. So here we are, this is how it would look. If you could make it perfectly, you'd have guide light trapped in the core and the photonic crystal solid material on the outside, preventing it from escaping. Okay, the very first one of these we made, of course this was another very exciting moment in the research. This was the structure that we made, and you can see that the glass, compared to the glass, is relatively thick, these tubes. You can see that these are how the tubes were stacked, because they haven't really melted very much. They're interstitial holes and so on. But nevertheless, it worked. We did our very simple experiment, the microscope and the white light source, and we looked and see what came through the fiber. Once a short length of fiber from the drawing tower, put it in the microscope, the first time we saw this, we almost didn't believe it. It's one of those. You've been working on something for 5 or 6 years, and the theory seems okay. You're not sure if you can actually make it. Maybe there's some reason why it's not going to work. There's a huge difference between doing some theory and actually making something work in the laboratory. It's much more exciting to make it work in the laboratory than do the theory, I think, because you hold it in your hand and it works. So there's no doubt about it. There it is. And in this case, depending on how large we made the structure, we drew it to different sizes in the fiber drawing tower. You'd get different colors guided in the core. It's a very nice red mode. Here's a yellow mode. And of course this illustrates a feature of photonic bandgap guidance, which is that the guidance is typically narrow band. It only works over you can control the bandwidth, the frequency range over which the light is guided. And you may think, well, that's a big disadvantage. You want a fiber, you want it to guide every possible wavelength. But actually, this is a huge advantage in some cases, because in certain experiments, you want to prevent light from being guided at certain wavelengths. You'd like to suppress maybe some spontaneous emission. You'd like to suppress some wavelengths that come out of a laser because you don't want them. So it's actually a very useful feature of these fibers that they are narrow band in some cases at least. Okay, that was the very first fiber. The losses for this particular structure were, pretty high. They were probably several decibels per meter in this case. So the next challenge was, having demonstrated this, was to see how low we could get the attenuation to go to. So what was the best value? And in fact, the record loss is just below 1 decibel per kilometer. So this is what's been achieved at Telecommunications wavelength. So this is a state-of-the-art. It actually is still 2004 where this was state-of-the-art, and it's still state-of-the-art. The company Blaze Photonics, which sadly no longer exists, had a fantastic technical team that really got into designing this structure, and they achieved this very low loss figure. You can see it's an extremely beautiful structure, very regular. Core is 20 micrometers across, and we have a closer look. You can see all the little different features, the interstitial shapes. Everything in this structure, including the thickness of the surround of the core, has been very carefully designed and modeled, and indeed it guides light at a wavelength of 1.5 micrometers with a loss of 1 decibel per kilometer. Anyone who doesn't know what a decibel is or doesn't have a feel for it, this means you can go for 3 kilometers, 3,000 meters, and you only lose half the light. So it's quite remarkable, I think, this very low loss. So just to think about what does that actually mean, to go 3 kilometers and only lose half the light. Well, let's look at it. Here is the core, the hollow core, and the cladding. You can think of the light as bouncing to and fro across the core, and in fact, by working out the angle here, you can count how many bounces the ray makes, and if you work it out for 1 kilometer, you get 2.8 million. You get about 3 million of these bounces, 1, 2, 3, 4, and so on, over 1 kilometer, for a core that's 20 micrometers in diameter at a wavelength of 1.5 microns. Okay, what does that tell us? Well, it allows us to work out the reflectivity for each of these bounces. How good is the mirror? And in fact, again, if you can do this in decibels, you get 0.35 microdecibels per bounce, or a reflectivity with a lot of nines there. I can't even read them. I think it's about 7 nines or something. But I would guess that this mirror is among the very best mirrors ever made. You know, if you compare it with multi-layer mirrors and so on, this is really amazingly good. But it's not just it doesn't just stop there. The reflectivity is amazing. It reflects for all angles of incidence and for all polarization states, because you have a photonic band gap. So these mirrors are remarkable, not only because the reflectivity is very high, but because they have this characteristic too. And furthermore, even more remarkable, every time you have a new lens, it's a new mirror. It's a new piece of material. It's not the same mirror you're using. You haven't made one mirror very carefully and you're using it millions of times. We're actually making a new mirror every time. So I think this illustrates that the photonic band gap phenomenon can in some cases be incredibly high performance. Really, really amazing compared to any conventional approaches. But of course there's always a downside. You know, you discover things when you make something like this. You discover that there are other effects come in and maybe make it more difficult to get the loss. And in fact, if you do a very careful measurement of attenuation versus wavelength, what is the loss at different wavelengths, you get a landscape that looks like this. There are very deep trenches in the loss down to very low values. In this case, 1.7 dB per kilometer. But in between, you have these mountains that rise very high. And of course, in order to see these features, the loss is very low here. Actually, look at the scale compared to most waveguides that you could make. These fibers have very low loss. So we're talking about 30 dB per kilometer is really very, very good loss figure. But compared to 1 dB, of course, it's very high. So what is going on here? Why are we seeing this? It turns out that these peaks, in fact, are caused by something that you would never see in a conventional optical fiber, and that is surface states. You're probably familiar with surface states on semiconductors, surface states on materials. But you have a photonic band gap in the cladding, and it's not so surprising, perhaps, that there will be surface states for light. And in fact, what's happening here is that the light is becoming phase matched to surface states, and you get very high attenuation at those points. Here's an illustration of this. These are measurements made by Georges Humbert in my group in Bath when I was there. He did some very careful measurements with changing the wavelength of the light and looking at the pattern coming out of the end of the fiber. So light was coupled into the core, and at one particular wavelength where the loss was very high, he saw that the light had transferred itself onto the surface of the core. And of course this light sees the interfaces, it sees the glass, and the loss is very much higher than when the light is in the hollow core. And you tune to a longer wavelength. The output here, we get a mixture of light in the core and light on the surface state, and at an even longer wavelength the light is confined in the core. So for this wavelength the loss was very, very low. In between, for these wavelengths, the loss was going up and getting very, very high. And this illustrates, in fact, that the fraction of light that's actually in the glass is changing dramatically, in this case with wavelength, and the loss, of course, scales according to how much light is in the glass itself. So here the loss is very high here, very low here. Now, having discovered this, and it's a very nice effect and interesting in itself, of course, then we go back to think about how could we avoid this, and in fact, by very carefully designing the thickness of the surround of the core, you can actually shift those surface states away from the guidance band. You can shift them over to regions outside the guidance band and get pretty low loss without any surface states over a reasonably broad bandwidth. This is work which originates, this is the paper that describes it, but this is a result that we did in Erlangen in my group. We make fibers there, we have all the facilities to do that. So this is quite nice. Here we have a bandwidth of maybe 300, 400 nanometers at a wavelength of 1550. And something else, just in case anyone's interested, people often ask what is the dispersion of the guided mode in the hollow core in a fiber like this. And these are measurements of an elliptical hollow core fiber which has a bit of birefringence. So you have two different polarization states, and depending on the polarization state you have a different dispersion profile. But the important thing is that for a hollow core structure, the dispersion is mostly anomalous. It's mostly anomalous dispersion that you get. And in fact, that's very much the same as for the modes of a hollow metallic waveguide. If you made a metallic waveguide to operate, let's say, microwave frequencies, you would find that the dispersion of that mode was anomalous across the entire, was always anomalous. But in the hollow core fiber, as we reduce the wavelength, what happens is that the light begins to leak. You begin to lose the bandgap effect, the bandgap gets weaker, and as a result the dispersion changes sign, so that you actually get a dispersion zero at some point across the transmission band of the fiber. So this is very characteristic of these structures. This means, of course, that you could support solitons if you wanted to in this range, and people have looked at that as well. The solitons require anomalous dispersion. All right, so that's basically the introduction to the photonic bandgap guiding hollow core fiber. There is another kind of fiber which is interesting because it offers much broader band guidance at the cost of higher attenuation, but nevertheless very interesting. And this is what we call the Kagome hollow core fiber. We use the word Kagome because it's based on a Kagome lattice. Here's a picture of one. Let's have a closer look. It's a little bit grainy, this picture. But I think you'll probably notice that looks like a Star of David. And in fact, it's the cladding structure of this particular fiber is the unit cell is indeed a Star of David. You can see, you can tie that, you get the structure, and that is the Kagome lattice that originates from Kyoto in Japan. It's a basket weaving, it's a way of making baskets. So this was discovered by chance, actually, by Feta Ben-Abi, a postdoc in my group back in about a decade ago. And the remarkable thing about this fiber was that unlike all the other fibers, hollow core fibers we've made, when you launched the white light into the fiber, you didn't see colors, you saw white light. So it seemed as if the fiber was able to guide all wavelengths, more or less, because the light coming through is white, and that was confirmed with measurements. This is a very old result, it goes back to 2002. So the attenuation figures are around about 1 decibel per meter, which is quite high. On the other hand, the bandwidth of guidance is extremely broad. So for some experiments, this is very advantageous. You may want to have an enormous range of wavelengths guided in some cases, and you don't care so much about the loss. It's quite an interesting structure to think about because actually it doesn't have any photonic bandgap. You can do calculations for the Kagome lattice and try and look for bandgaps. And here is a diagram of density of states. So the dark regions are regions where the density of states is high, and the white regions are where the density of states is low. And there are no photonic bandgaps at all in this structure. So whatever the guidance mechanism is, it's not based on the presence of a photonic bandgap. This is wavelength, and this is propagation constant, essentially. But we can, on this diagram, you can identify certain features. So there's obviously some horizontal line here, and that's associated with light that is guided as resonant in the large hollow regions. Okay, this dotted line. This is the air line. So above this line, the light is unable to propagate in air, but down here it can. So you're allowed to form resonances in the hollow regions. So this is what this line corresponds to. And then if we go to this, the line down here, this dotted yellow line is resonances in the smaller hollow regions. And if we have a look at these, you see there's some vertical lines on the plot. These vertical lines are associated with resonances on the glass strands themselves. So the light is now concentrated in the glass, and they shoot up like this. So up here, the resonances in the glass are completely guided by the glass because the refractive index is above that of air. Down below this line, the light is able to propagate in the air, but so it's like, these are like me resonances. These are resonances which are able to radiate into the hollow regions down below. There's all sorts of interesting features, and so you can also have higher order modes of these glass webs too. There's all sorts of interesting features here, and you can do modeling on this. And so here is wavelength versus loss. And you can see there's some very interesting peaks in the attenuation. In fact, those are associated with resonances of the strands of glass. So here's a single lobe resonance across the strand, here's a double lobe resonance across the strand. And what's happening is the light in the core is coupling very strongly to these resonances and leaking away, so you get a lot of attenuation there. So just to summarize that, we have hollow core fibers. We have two main kinds of hollow core fiber. There's the photonic bandgap kind and there's the Kagome kind. And the photonic bandgap hollow core gives you typically fairly narrow band guidance, but extremely low loss, which can be as low as a decibel per kilometer. And the dispersion changes sign across the guidance band. So this is the main features of this structure. The Kagome fiber, on the other hand, gives you broadband guidance. The dispersion is very low, it turns out, across the transmission band, which is kind of nice, useful, and can be useful. The losses, though, are quite a lot larger than in this case. They're around about 1 decibel per meter. Okay, so I said here I'm talking about structures where the delta n is negative. Of course, that doesn't have to mean that we simply discuss hollow core structures. There could be a structure which has a solid core where delta n infinity is less than 0. And so I'd like just to introduce the old solid bandgap fiber, so where the structure is made from solid glass. And this is kind of an interesting result that we came upon when we were thinking about this. You can actually get, in these two-dimensional fiber structures, you can get photonic bandgaps with vanishingly small refractive index contrast. You may think that's crazy. What's he talking about? Everyone knows that photonic bandgaps require very large index contrast. Well, that's true in general, but in this specific structure, it turns out you don't need large index contrast to get a photonic bandgap. And to kind of explain this, I'm going to take you into reciprocal space. I don't know if any of you are used to working in reciprocal space. It's like sort of walking around upside down all the time. But it's actually very useful to be able to do this. So what I'm going to do here is just introduce this wave vector space idea. So we're looking at wave vectors. We're not looking at distance or position. We're looking at wave vectors in different directions. This is the axial direction, the direction along the axis of the fiber. And of course beta is the parameter. I think you're probably familiar with that by now. And then there's a transverse wave vector, which is the wave vector in the transverse plane of the fiber structure. And here's the fiber structure we're going to look at. It's made from two materials, N1 and N2. If we think about material, let's say refractive index N1, which is the larger refractive index, then you know that the wave vectors in all directions will have the same value. It will be the vacuum wave vector times N1. So we get a circle. So the allowed directions of wave vectors lie on a circle, actually a sphere, but in this picture it's a circle. And the other region is N2, where the refractive index is lower, and this time the circle has a smaller diameter. What this diagram allows us to do is to select the value of beta, and like I said right at the beginning of the lectures, this value of beta is conserved throughout every region of the structure. Once you've set that value of beta, it has the same value in all the regions of the structure. So this means that all the other wave vectors that are allowed in here, they have to have the same value of beta. This means we can put a construction line up, and we find that in region 2, for example, we have a transverse wave vector which has this magnitude, and in region 1 we have the yellow one which has a slightly larger magnitude. Now just think about what happens if we make beta larger. If you make beta larger, you can see that the ratio of KT2 to KT1 is changing, and in fact, as beta tends to K times N2, which it tends to the edge of this inner circle, then the ratio here tends to infinity. So this effectively is telling us that in the transverse plane, the ratio of refractive indices is tending to infinity. So although the refractive index contrast itself as N1 to N2 may be very close to 1, if you go to the edge of the circle, we can get ratios of wave vectors which can be very, very large. So this allows you to get photonic bandgaps, in fact, just this simple effect. So what do we do? Well, we wanted to make a structure like this, where instead of having hollow channels in the cladding, we filled these with some germanium doped glass. That's the idea, which has only a refractive index maybe 1% above that of the silica. So the grey regions are silica, and these coloured regions are germanium doped glass. And the core is formed by leaving one of these out. So the core index is lower than the refractive index in the strands. Germanium increases the index of the glass. So for this to work, we have to be sure that the mode in the core existed in a region where you had a photonic bandgap. That's to say, a unit cell in the cladding had a transfer matrix where the eigenvalues had real values. Okay, so this is the concept. The way we made this was to, first of all, make a photonic crystal fiber preform. So a honeycomb lattice. This is 0.2 millimeters, so this is quite large scale. These holes are large enough so that we can actually push a conventional optical fiber into the holes. This is a multimode fiber. It's got quite a large core, as you can see, and we thread it, we push it into the hollow channels, and then in the actual center of the fiber in the core, we put a single mode fiber in there that has a much smaller core, and then we draw it down, and we ended up with this structure on the right. You can see that the single mode core is very tiny to start with, and when you've drawn this down to an actual fiber, this is much smaller scale, you really can hardly see the remaining core. It doesn't really guide light anymore, whereas the large cores in the multimode fibers you can still see them in the structure. Okay, so how did this actually work? Well, it was a very, very beautiful experiment. I think the results were really very, very nice. This was the transmission through the fiber as a function of wavelength, and you can see we had good transmission over a reasonable in the infrared here. But then there were these very sharp dips in transmission, and it came up again, very sharp dip in transmission, came up again, very sharp dip, and so on. And by coupling white light into the core, in fact we used supercontinuum fiber source to do this. By coupling white light into the core and using filters, we were able to identify what caused these dips in transmission. So for example, if we go to this particular dip, and you have a look at these strands of glass in the cladding, and look at the field pattern, it turned out this dip was caused by the presence of resonances in the germanium doped glass rods in the cladding here, with two lobes. So this was an LP11 mode. And the next dip in was a green one with 3 bumps. So the LP02 mode became phase matched to this. So the light goes into the core. You can hardly see from here where the core is. I think it's there. And phase matches to certain wavelengths and phase matches to modes of these strands. And there's a green 3-lobe one, and then further in we get, and you don't see it on the diagram, there's a 4-lobed blue mode, which is the LP21 mode. So these are regions where the light in the core becomes phase matched to resonant states in the cladding. In fact, these, of course, are me resonances. These are not guided modes. These are, as I say here, these are not bound waveguide modes. They're actually me-like resonances. They're free resonances. If you put light into this resonance, it will leak away with a certain lifetime. So it doesn't have infinite lifetime. But I think a very nice illustration of how this works. And you can make more complicated structures. Many rings to bind them. This is a quotation from Lord of the Rings, kind of. But this is a structure I showed you in one of the very first slides, where we have rings of germanium doped glass. And this again was a new kind of photonic bandgap fiber, where what was done here was to engineer the photonic bandgaps in the cladding so as to reduce the number of cladding states, and it's quite a nice structure, I think. Some very beautiful pictures of the modes that exist on these rings in the cladding. Okay, so I think what I'll do is I'll talk about this, and then I'll have a break. Yeah. Okay. So this is something kind of funny and I think rather amusing and unexpected. I call it anomalous cornering. So what do I mean by that? Well, you'll understand, I hope, when I finish describing it. It's about bend loss. It's about what happens when you bend a fiber. Of course, unlike many other waveguide structures, you can actually bend an optical fiber in any direction you want and see what happens. So if we just think about a conventional fiber, a step index fiber it's called. The index steps up and steps down again. It's a step index fiber. So this is the center of the core. Refractive index in the core is higher than in the cladding. And the guided mode index, so this is a refractive index in the vertical scale. The guided mode has an index which lies in between the cladding and the core. So that's very well understood. So when the fiber is straight, this is what we see. If you bend the fiber, however, you bend it, then you're going to find that on one side the optical path length increases, so the refractive index goes up, the effective refractive index goes up. On the other side, the fiber is compressed, so the path length drops and the refractive index drops. So if you bend the fiber, the right-hand bend, you bend it towards the right, you'll find that the refractive index goes up on this side and it goes down on this side. So bending the fiber has exactly the same effect as putting an electric field across the semiconductor. The band structure becomes skewed, it ends up being at an angle. So instead of this distribution of index, we get a distribution of index that looks like this. It becomes skewed. So here's the guided mode. And you can see that if you bend it like this, the light has the possibility of tunneling through this barrier and escaping. So the barrier, instead of being infinitely thick, it becomes a finite thickness. There are some states here the light can tunnel into, and indeed this is what happens. If you bend the fiber towards the right, the light will leak out through the cladding and escape. That's a pretty simple picture. Now what I want to do is consider what happens if we have photonic bandgap guidance, in particular photonic bandgap guidance in one of these all solid bandgap fibers. Once again, refractive index, and here this is the picture we get for a straight fiber. So refractive index, we have a lower band edge for refractive index, we have an upper band edge for refractive index, and we have a guided mode that sits somewhere in between. So the guided mode is like an intraband state in a semiconductor, and the photonic bandgap extends between these 2 points. So I think that's pretty clear. The next question is what happens when we bend? And this is where we get anomalous cornering under some circumstances, which is really quite strange. So the whole structure becomes skewed, just like I showed you before. Let's suppose we had a guided mode that was close to the lower band edge, the valence band edge, in the language of semiconductors. Well, we bend the fiber to the right, then we would get leakage through the band, with leakage from the guided mode would be able to leak out towards the left because there are some states here. This is the pass band. So the guided mode is able to leak through the barrier and escape into the pass band of the cladding. Nothing surprising. You bend towards the right. You're driving a car. You turn towards the right. You're thrown towards the left. So that makes sense. But if we, however, have a guided mode close to the upper band edge, and we bend in the same direction, this time the states that the light can see are on the right-hand side. So you get leakage towards the right. So it's as if we've changed the sign of the mass. The mass has become negative, or you can look at this in various different ways, but it's a very strange effect. You bend the fiber towards the right, the light leaks out in the anomalous direction, which is why I call it anomalous cornering. It's as if one of these guys in Formula 1 driving around the corner all of a sudden was thrown out in the wrong direction, which I think would be very, very, very strange feeling for these people. In fact, the first time I talked about this, I was in Sao Paulo, in Brazil, and in fact the Formula 1 races were going on at that time, so it was quite, that's why I had this picture. Okay, I think that's a good point to have a break, and take any questions.
Are there questions? Yes?
I have a question about the all solid bandgap fiber. Yes, you use some solid instead of air.
Yeah.
But there is still a bandgap with that. But the propagation constant should be larger. It should be large if you want to get the bandgap.
It's certainly true that let me just get a picture here. It's certainly true that if to have light propagating in the core, the propagation constant has to be larger. The propagation constant in the core will be just slightly lower than let me rephrase this. To get a guided mode in the core, you have to make sure the light is propagating in the material that the core is made from. So this means that the beta value in the core has to be less than the wave vector in silica glass. In other words, beta has to be less than k times the refractive index of the glass in the core. So the beta value for the guided mode in the core is certainly going to be larger than in the hollow core case. But the band gap, you can design that to be anywhere really, just depending on how you what size these, what the pitch and spacing is, what the size of these features is, and so on. You can move the band gap around. And in fact, something I didn't say was that if you imagine this is, say this is refractive index going upwards, and let's suppose the band gap, the top of the band edge is here, the bottom of the band edge is here. You can also say, well, what value of refractive index gives me a resonant state actually in the core itself? And of course that's somewhere else, that has some other refractive index. So the guided mode might be here, and the band gap might be here. And in order to get a guided mode in the core, you have to be sure that it's more or less like this. If it was like this, you wouldn't get a guided mode. If it was like this, you wouldn't get a guided mode. The refractive index of the mode in the core has to coincide with the band gap. And that's an additional condition that you need in order to get guidance by the band gap effect.
In this case, the loss will be much larger than the core is.
Than the hollow core?
Yeah.
The losses aren't too bad actually. I mean, the loss here is 20 dB per kilometer. It's been demonstrated. So in fact, the losses are not too bad. I don't know what the record is, but I think this might be the best loss that's been reported for these structures. And I would guess that with a certain amount of work, you could get losses that are approaching that of the best telecoms fibers. One of the problems is that the band gap is not so strong, because the refractive index contrast is small. So you need to have lots and lots of layers of holes to keep the light well confined. So it becomes a challenge. Can you get enough layers to get actually very low loss? And that's probably the reason why the loss is relatively high here.
Are there more questions? From the fabrication standpoint, when you draw so long fibers, is it technologically challenging to do it, so that the structure remains so uniform?
Yeah. So how easy or difficult is it to make very long lengths? It's relatively. You need to have very good control of the equipment, of course, but the process is intrinsically very stable and very reproducible. And in the work where we showed this loss of 1 decibel per kilometer, we were drawing kilometer lengths of hollow core fiber. So it wasn't just a short length; we were pulling hundreds and hundreds of meters. Because in order to measure that loss, you need to have a kilometer of fiber. You can't measure it otherwise. So technologically, it definitely works. It's completely. It would be quite straightforward to pull kilometer lengths of hollow core. So I think there's a very good chance that hollow core might end up as the fiber that people use in telecoms for long-haul communications in maybe 10 years' time. And so it's hard to predict the future, but it's a possibility at least.
Are there more questions? If not, let us thank our speaker. And we will reconvene in 10 minutes.
10 minutes, right. For the hollow core fibers, and then talk about a few miscellaneous things that have been going on more recently. And finally, I'll talk about tapering, which is a way of changing the structure after you've made it, which turns out to be very useful in some cases. So the first thing is gas vapor devices. And this is the making use of the opportunity that the hollow core gives you to put something in the empty space. We've already established that you can guide light in vacuum, but of course you can put something in the vacuum, and gases and vapors, of course, you can put in there. And why would you want to do that? Well, you would then be able to make use of the guidance of a single mode in the gas over long distances. And of course the refractive index of a gas or a vapor is very close to 1, so it's difficult to make a waveguide with them, if not impossible. And one particular application here is that of enhancing nonlinear interactions, nonlinear effects with gaseous media. And now if you want to enhance a nonlinear interaction, you have to optimize various things. And it's very simple actually. I mean, if it's a nonlinear effect, typically what you want to do is optimize the nonlinearity. You want to have a large value of nonlinearity in the material. You want to optimize the path length, so you accumulate a very big effect over a long distance, and you want to enhance the intensity probably for an intensity-dependent nonlinear effect. Most nonlinear effects are intensity-dependent, so you'd want to optimize the power over the area. So the important things here would be the nonlinearity, which is provided by the gas in the hollow core, the path length, which is provided by low loss in the fibers, go long distances, and the area. We'd like to make this as small as possible, and we prefer that it be single mode, because if it's single mode, you have much better control of your experiment. So very simple. What does that get us to? Well, I'm going to go back to this picture. There's Lord Rayleigh, John Strutt. That's what he used to be called before he became Lord. If you wanted to enhance that thing I just talked about, to enhance the intensity and the interaction length, you'd like these both to be large. And suppose we try and do this with a lens. We've got twice the Rayleigh length, actually, that is, and spot size. Well, think about this region. What's the intensity? The intensity is proportional to 1 over a squared. 2a is the spot size. Okay? And the interaction length turns out to be proportional to a squared over lambda. So that you get a longer interaction length for if the wavelength is small, and that kind of makes sense. If lambda goes to 0, diffraction doesn't take place at all. You lose diffraction. So the Rayleigh length will become infinite. But of course we can't work with 0 wavelength, that would be crazy. But however, what's interesting is the product of intensity and interaction length in this case turns out to be independent of the radius of the spot, because the a squares cancel. So this is telling us that there is no advantage in using a lens to optimize this product. Of course, there is an advantage to using a lens because the device becomes shorter, but in terms of diffraction and so on, there's no advantage for this value of this product. And this, of course, we look at hollow core. In this case, it's completely different, because we have an almost infinite Rayleigh length. In fact, and the intensity goes as 1 over a squared, a being the radius of the core. The absorption length goes as 1 over the loss, which has nothing to do with the radius. They may be related in some way, but this can be very, very long. So the product of this thing is simply proportional to 1 over a squared and 1 over the loss. And if you compare the product of these two things, compare this, so we fill the core with some gas, and we're interested in a nonlinear interaction, you can enhance the interaction by 10 million times. It's better than a focus beam. You know, this is an amazing number, I think. I mean, in the field of nonlinear optics, I mean, usually we're kind of struggling to get a large enough nonlinearity, and even small increases, 1.5 or a factor of 2 in a nonlinearity can transform a field. But here we have 10 million times higher in interaction strength between the gas and the light. So you can probably imagine this is really quite revolutionary in terms of the things you can do with it. So one example of what you can do with it is to have a look at, we've been looking at this as well as other groups. This is my former postdoc, Philip Benabi, who's still in Bath, a paper from 2004, the first report of stimulated Raman scattering in hydrogen gas. And the fiber we used for this experiment, looking at rotational stimulated Raman scattering, I'll explain this in a moment. The fiber we used was one where the guidance band was 150 nanometers wide, with the center around 1 micron, so we wanted to use a neodymium YAG laser, 1064 nanometer wavelength. And here's a picture of the fiber structure itself. The loss is not too bad for this particular wavelength range, around about 75 or 60 dB per kilometer. Important, though, that the guidance band is restricted in its width. So what we wanted to do was to look at the rotational Raman scattering, and that's basically, for hydrogen, it's the molecules are rotating, and they rotate at a certain rate, which is quantized, and the frequency is 18 terahertz, the rotational Raman scattering. And the light goes through the gas, and what it sees is this rotating molecule, and the rotating molecule phase modulates the light going through. You get a phase modulation of the light which creates sidebands. And these sidebands are the Raman scattering bands, the Stokes and the anti-Stokes. Simple way, classical way of looking at Raman scattering. Of course, you need to do a full quantum description if you want to understand all the details. Now, the nice thing about this fiber is that if you put the pump light in at 1064, the Stokes line, shifted by 18 terahertz, still is within the low loss window. And so is the anti-Stokes line. But we're mainly interested in the Stokes here. Okay, so if you know anything about Raman scattering in hydrogen, usually it's completely dominated by vibrational Stokes. And that's this particular vibration of the molecule, where the stretch vibration. It runs at a much higher frequency, about 10 times higher, and it's much, much stronger. You get much more gain with this transition. And it's actually very difficult to get rid of this transition and study the rotational Raman scattering, because you need some kind of complicated filtering, maybe a fabric cavity to get rid of this frequency. It's difficult, very difficult to engineer the experiment. But the fiber gives it to you almost for free, because this frequency of the vibrational Stokes sees enormously high loss in the fiber. So it simply never appears. You never see any vibrational Stokes conversion in these fibers, except spontaneous, of course, which is always there, but it never becomes stimulated. So you're able to study rotational and not be bothered by vibrational Stokes. Okay, what are the results like? Here are some of the results, again, from this early paper. The pressure of hydrogen in the fiber was 7 bar, 7 atmospheres, and the loss was of the order of 1 dB per meter in this particular case. So here's one result. This is 35 meters. That's a very long length, interaction length. 35 meters of fiber filled with hydrogen. And this is the energy of the pulses coupled in. And this is from a microchip laser, so these pulse durations are about just below a nanosecond in duration. And the energy is of order nanojoules. And what we found was we got a threshold energy for stimulated Raman scattering of around 5 nanojoules. And if you look in the literature, this is 1 million times lower than ever previously seen in a single pass experiment. A single pass experiment, you send the pulse through and that's it. A multi-pass experiment, it goes back and forth many times, so you get an effective path length that's much longer than the actual size of the cavity. But in this particular case, it's just one pass through, and we get a threshold, very low threshold. You will notice that the transmission, these are normalized units, the transmission is not so good. This is 50%. So the conversion, although the threshold is low, the actual conversion efficiency is 30%. And the reason for that is that the attenuation of the Stokes light is not as high as this, but it's high enough, over 35 meters, so that you lose quite a lot of the light. You can do the experiment again, this time with a 3 meter length, so it's 10 times shorter, and this time the threshold has gone up by a factor of 4, now about 20 nanojoules, but in this case we get almost perfect conversion. We lose very little light because of the shorter length, and in fact, if you count the number of photons going in, the number of photons per second going in, we have the same number of photons per second coming out. Of course, you have what we call the quantum defect. That's the loss of energy to the molecules. But basically, the quantum efficiency is close to 100% in this case over that length. So we have almost perfect conversion of energy from the light photons going in to the photons coming out. It's a very nice result, and also very useful in applications potentially. So that's Raman scattering. I'm going to come back to another experiment, a more recent one, in a moment in Raman scattering. But there are other things you can do, of course, with hollow core. And another thing you can do is look at what is known as electromagnetically induced transparency, which is a quantum mechanical effect of the interference of two pathways in a 3-level system. which effectively mean that the transmission attenuation can be reduced to nothing when you'd expect it to be very high. And this was done, in this case, with acetylene gas put into the fiber. To do this experiment, you need two sources of laser light to excite two different transitions in this three-level system. It's kind of hard to read it from the side here, actually. But you feed these two frequencies into the fiber, and one of them is a probe laser, and the other is a kind of pump laser, a high power laser, and a low power laser. And then you measure the transmission spectrum through the fiber using various electronics, and the results of all this. Here we are. There's the probe. This is the pump. This is the high power. This is the low power tunable pump. And here are some of the measurements. On the top, this is the transmission through the fiber as a function of wavelength. Acetylene has a very complex absorption spectrum in the range of telecoms. It's 1.5 microns. It's a lambda system in this case. You can also have a V system. These are two different systems for EIT. And the two pathways are from here to here and from here to here. And the quantum interference is between these two pathways. So if you drive these two things correctly, you can get transparency. Okay, so we did experiments. This was the R11 line. So we were probing this line. This is the transition here, this one. And then we put in the pump line, the P13. In the presence of this, you find there's a sudden increase in transparency in the middle of the absorption dip. This is a signature of EIT, and you get 70% transparency, which at the time was a record for this particular kind of experiment. This is an example of how relatively easy it is to do what used to be quite difficult experiments, relatively easy to do in the fiber, because the light is guided in a single mode over long distances. It's extremely well controlled, and you know exactly what you're doing. Something else you can do, surprisingly perhaps, with these fibers is splice them to standard single mode fiber. And this is an example of one of the experiments done some time ago now. This allowed us to produce a hermetically sealed inline gas cell. So there's gas in the fiber, and it's spliced at both ends to standard solid fiber. Here's a picture. There's the gas-filled fiber. These are the splices, and this is single-mode fiber, conventional single-mode fiber at the pigtails. The splice losses in this case were about, I think, 2 or 3 dB. But I think nevertheless it's a nice way of maybe having an inline device that you could potentially use in an application. Okay, so this is going to be a little more advanced, so I hope I won't lose too many of you here. But I just wanted to show some of the recent work that we're doing in Raman scattering in hydrogen. One of the features of Raman scattering, of course, is that it doesn't just work in a forward direction, it can also work in a backward direction. You can get phase matching to the backward direction and have backward Raman. Backward Raman experiments are difficult in gases using conventional approaches. Very difficult to control them, but in the fiber it's extremely easy actually. And this is just going to show you some recent results that were published at the CLEO meeting in Europe a month or so ago. The experiment had 2 stages. We had a pump laser, which was a neodymium laser. Some of that pump laser light was coupled into a length of hollow core fiber filled with hydrogen. And in the process of the pulse going through, we generated some Stokes signals. So you generated a frequency shifted signal. This is rotational Raman scattering again. And we take this Stokes and we feed it back. Actually, there's a filter here as well to get rid of the pump light. And we feed the Stokes pulse into a second piece of fiber, backwards. And the other part of the pump light comes straight through and is coupled into this second piece of fiber going in the opposite direction. So we're pumping the system from the left, and we're seeding it with this pulse from the right. So this is the backward Raman interaction that we're going to explore. So what we see in this case is the pump pulse comes in, here it is, going in this direction, and the Stokes seed pulse coming in backwards. And these two pulses collide. They come together and they collide, And the moment where the small pulse collides with the big pulse, this feels a huge amount of gain and grows in size. And what you see is really very interesting. And again, I could spend a whole lecture talking about this, but there isn't time. I just wanted to show you this. What we see is that the Stokes pulse goes in, and as it grows in strength, it gets narrower and narrower and narrower, and it ends up being, I think the duration, does it say it here, something like it's a small fraction of a nanosecond, so it ends up being very, very short. And in fact, something that, for those of you who know about Raman scattering, there's a thing called the T2 time, which is the coherence time of the oscillations of the molecules. They will be in, these molecules will be vibrating or spinning in this case in phase, and they'll do that for a certain length of time, and they're called the coherence time, and then they'll collide with themselves and collide with the walls and so on, and you lose the coherence. The coherence is necessary for Raman scattering to work, and in fact this pulse is a lot shorter than the coherence time. And the reason you can get such short pulses is because of the intense stimulated interaction, so that you can get things that happen more quickly than T2 in this case. It's very, very nice, and there's some very exciting results coming out of this because of the very beautifully controlled experiment that we had in this case. I just love these equations. I'm not going to talk about them, but I think the theory of Raman scattering is so beautiful. You've got the electromagnetic equations, and you've got the equations describing what the molecules are doing. And this is all about quantum optics here, quantum mechanics. And this is about classical electromagnetism. And the two of these things are coupled together. So it's a very beautiful theory, but there's no time to talk about it today. I just love the equations so much I wanted to show them to you. All right. So you do see some funny things in this effect. If we look at time-space, and you may find this surprising, but there's a very good explanation for it. I'm going to now give you a time-space diagram, and this is the position in meters in space relative to the leading edge of the seed pulse. So the seed pulse is coming in, we're staying with the seed pulse, although it's moving, we're actually in the same reference frame as the seed pulse, moving along with it, and taking a picture, taking a video of what's going on. The pump light is coming towards us very fast, so it's moving towards us in this frame of reference, and the edge of the seed pulse at 0 is not moving at all. Okay, so this is the backward Stokes seed, this is the forward pump. These are numerical modeling of those equations. This is what happens when we send a certain kind of seed pulse, a Z-squared pump pulse in. Here's the seed pulse coming in. You can see it interacting with the pump pulse. It eats away at the energy. It takes the energy from the pump pulse and grows more, grows more, and grows more. And you can see it's quite a complicated interaction. But the most surprising thing about this, that you may find surprising, is that the pulse is actually advancing, going faster than it should. In fact, it's going faster than light. Of course, it's not actually. I mean, we're not contravening, we're not breaking the laws of physics here. What is happening is that the front edge of the pulse sees very high gain, and what you're seeing is a pulse reshaping. So the front edge of the pulse gets lots and lots of gain, and so it grows more strongly than the back edge, and as a result of that, the overall pulse appears to be going faster than the speed of light. But nevertheless, quite a startling kind of picture. These effects are well known in systems in the presence of gain, or indeed loss. You can get things like this happening. If we make the pump pulse much sharper, so instead of a Z-squared pulse, we use a super Gaussian pulse with a much sharper leading edge, so it has a different shape, then we no longer really see this speeding up of the pulse, because the leading edge is so sharp, you don't see this effect anymore. Okay, so the next topic, moving now to something completely different, is particle guidance. We have a hollow core, we have light in the hollow core. The question is, could we pick up a small particle, or maybe an atom or something like that, and use the radiation forces and the trapping forces of the light to trap the particle in the hollow core and to propel it, to accelerate it along the hollow core. This is what this is about. And this, of course, this work dates back to the pioneering work of Arthur Ashkin, who for some very strange reason didn't win the Nobel Prize for this, although he did all the initial work. Somebody else did. I think he should have won the Nobel Prize for this, but didn't. So this idea was that you can use laser light to trap small particles, and this is a focused laser beam, and this is a small particle sitting in the laser beam. It turns out that if you look at the refraction of the light at the surface of the particles and reflection, and do a careful study of this, that you find that there's a radiation force that pushes the particle upwards, and curiously, because of the diffraction of the laser beam, the trapping force keeps the particle in the middle, but also pushes it backwards a little bit. It's kind of funny when you see this, but if you look at it, you'll discover that there's a component of force pushing downwards. It might also be gravity, but this typically is so small it doesn't matter. Anyway, the result of this is that the particle finds a position, stable position, where it just sits. And then you can move the laser beam and move the particle around. This is why it's called a tweezer. So the question that we were asking, was, what would happen to these forces if we had a beam that didn't diffract? If we had a non-diffracting laser beam? What would happen if we could just switch off diffraction? And of course this would be an empty space. There is no way to do this. Empty space has an intrinsic diffraction because of the spherical shape of the dispersion surface for free waves. But in the hollow core fiber we can do this for the first time. We can actually switch off diffraction and we can maintain constant acceleration on a particle over very long distances. So it's something completely new that we couldn't do before. Okay, well, the very first experiment, which was done back in 2002, actually quite a long time ago, I'm going to show you some more recent stuff, but this was a very crude experiment actually. Here's the hollow core fiber. I call it catching the dancers because what we did in fact was have a bunch of polystyrene spheres on a glass plate, and these tend to stick to each other, so to stop that we put a transducer and we drove it with an electrical signal, got them to dance. Here they are dancing. The laser light coming from below. Every so often a particle is trapped and pushed up into the hollow core. That's the concept of this experiment. And here is a picture of a side view of the fiber. These are the parameters of the experiment: 5 micron diameter polystyrene spheres, 80 milliwatts of power. And these are a sequence of frames of a video where you can see the little dot, I think, going up. That's the particle trapped in the hollow core being pushed along by the light. And of course the core is filled with air, so there are some viscous drag forces. And for this particular power, in this particular experiment, the actual velocity of the particle was 1.5 centimeters per second in this case. Of course, if you could arrange that the core was vacuum, that you remove the air completely, then at least then the drag forces would become close to zero, and the particle would continue to accelerate as it went along. So it would be like a kind of laser-driven rocket. So where you could use light to accelerate a small particle to huge speeds. I mean, it's potentially even relativistic speeds. Okay, well, one application that has interested me for a number of years is applications to cytometry, to the measurement and studying of living cells or vesicles in the biological area. In this particular case, we want to fill the fiber with liquid because cells don't live really in vacuum terribly well. So you fill the fiber with liquid, and if you could do that, you could do experiments like this. You could have a blood cell which would be pushed up into the liquid-filled fiber, and you could maybe hold that in position with a fluidic counterflow, so the fluid coming back, pushing the particle down, the laser light pushing it up and holding it in position. And then you have a highly controlled microenvironment inside the hollow core where you could start to do things. You could, for example, fill the fiber with biochemicals in aqueous solution, maybe pump them down using microfluidics. You could use this for studying anti-cancer drugs, for example. This might be a cancer cell. You could observe what happened. And by looking through the side of the fiber, you could, for example, activate the chemicals using some other wavelength of laser light from the side. You could pick up fluorescence. You could even study the metabolism of the cell by picking up the chemicals that the cell is producing and analyzing them down here. So you could put light on the cell and see how the metabolism changes and what the byproducts of the cell reaction are. You can study a cell in enormous detail, like a little chemical factory. Of course, that's what it is. This allows you to do that potentially. So I got very excited about this as a new way of studying living cells, and recently we've been doing some much more carefully controlled experiments on this. And in fact, this is an experiment, an initial experiment, using a fiber which was filled with deuterium oxide because the attenuation is lower for this particular experiment. And here is a picture of the fiber, and it's designed so that when we fill the fiber with D2O, the band gap shifts to the wavelength where we want to do the trapping. The wavelength where we want to do the trapping of the light was 1064 nanometers. So I think earlier in the lectures I talked about this scaling law. So we used this scaling law to work out where the band gap would shift to if we filled the fiber with D2O. So then we had to make the fiber so that when we filled it with liquid, it would guide the wavelength we wanted to. So there's a certain amount of work involved in making this happen. But in the end, we got a very nice single mode guidance in the liquid-filled fiber core. And then the experiment involved, well, we wanted to do this very reproducibly. We wanted to be able to pick up the particle we wanted and guide it into the fiber. So what we did here was to have a second laser, a load laser, that picked the particles up. So this is the end of the fiber, this is a glass plate, this is a glass plate, and there's a pool of liquid here. So this is covered in liquid, the end of the fiber. And there's a few particles sitting here on the substrate. We can pick them up with the laser with tweezers, move them up to the entrance, and then use the launching, the guidance laser to push them into the fiber. And then we have various cameras. We can look from below. We can look through a mirror here, partially reflecting mirror, and look at the end face of the fiber. And we can also look through a camera through the side of the fiber to watch the particle once it's inside. And then at the other end of the fiber, the far end of the fiber, we've got a reservoir with liquid, which we can move up and down, changing the pressure. And this is then fed in through a liquid cell. It's fed into the fiber. And again, there's another camera here looking at the output face. So by varying the pressure, we can vary the flow rate of the liquid through the fiber in the opposite direction to the light. And here now are some pictures of the experiment. This is the loading of the particles. So looking through the camera, we first of all pick up a particle. Here it is. You can see it glowing. It's picked up. It's moved across and up towards the fiber. And finally, it's moved up to the hollow core. There it is sitting at the hollow core. And then we switch on the guidance beam to push the particle in. And this is a side view of the side of the fiber. The core started here and went down to here. This is the particle that we're going to push into the hollow core. And actually, it was rather fun. The particle was being pushed from the left, and the liquid was flowing out of the core, so the particle was actually spinning. You could see it spinning when it was sitting there stationary. And then you turn up the power, and it goes into the fiber. And here is a sequence of the scattering seen from the side of the fiber of the particle moving along. And this is time, so 1 second, 2 seconds. It's fairly slow, the movement. But you can see it moving along through the liquid. And of course, we have a balance between viscous drag and the radiation force of the light. And in this particular case, it moves at a certain speed. So with this experiment, we have a very, very nicely controlled system because we have a single mode guide here, so that the light is very, very well understood. We know exactly what the light is, the intensity of the light, the distribution of the light. And we know the size of the particle, we know the flow rate, and so on. So you can do some very nice measurements. For example, you can do a measurement where the fluid flow is adjusted, or the power of the laser is adjusted so that the particle is stationary. So we have some fluid counterflow, and we have the radiation pressure of the light, and just by adjusting the power of the light, we can make the particle sit still, be stationary. So these dots are the result of a series of experiments for different particle sizes. This is the pressure gradient that's driving the liquid. So the more pressure there is, the faster the liquid flow. And this is the power you need to keep the particle stationary. This was very reproducible. You go back to these points and they would be there again. So very nice and reproducible experiment. So this is the first time anyone has shown that you can hold a small particle stationary and have with light and have liquid flow backwards past the particle. So it proves that you could actually load the liquid with chemical and have it come past the particle, and maybe do some chemistry on the particle and see what effect that has. We also did an experiment where we measured the particle velocity as a function of power with zero fluidic counterflow. So it's a slightly different experiment, and once again we got very reproducible results, it turns out, which actually agree very well with the theory if you do the theory of this. But kind of excited about that, because I think it could be very useful to chemists and biologists and all sorts of people who are working with small particles. Finally, a long-term goal here is actually to make small particles go extremely fast. I hope in the end up to relativistic speeds, because I think if you can get a particle in a hollow core to travel at huge speeds, then there are some very interesting physics in the interaction between the particle and the surfaces of the core. You've probably heard of van der Waals forces. Well, there are other kinds of forces that are a bit like van der Waals forces that happen between solid materials when they're moving very, very fast relative to each other, and they're very close to each other. So it's an experiment that I'm really looking forward to. It's a very difficult experiment actually to make it work. That's my phone. But if you could do it, you can do the calculations very simply. You can work out the force on the particle. You've got a certain amount of power. You can put in the parameters of the system and so on, and you can estimate the velocity you would reach after a certain distance for a certain power. So if we do a simple calculation, and this may or may not be maybe out by an order of magnitude, but it's approximately correct. If you have a particle 100 nanometers in diameter with a certain density, and you have a fiber that is evacuated, so there's no gas in here, 10 micrometer diameters, these are pretty reasonable figures. With 1 watt of laser power, which is quite a modest amount of power, you could easily guide a watt, you could guide 100 watts in the core actually, then you would reach 28 kilometers per second after 100 meters, which I assure you is quite fast. It's the kind of speed that people doing people who do fusion experiments for energy production, they would like to make particles go this fast. So it's, and they have great difficulty in reaching speeds like this. So this could even be a way of maybe doing fusion in the future with small particles. Okay, so that's all the stuff I was going to talk about in connection with hollow core. Now I'd like to move on just to some miscellaneous things. In fact, just 2 topics it turns out. One is the topic of nanowires, which is potentially relevant to metamaterials and to actually quite a few different fields. Also to the liquid crystal work you heard about as well. So metal nanowires. And the idea here is, could we somehow introduce very thin gold or silver or other metallic wires into the fibers and explore what's going on. Why were we interested in this? Well, mainly because a very narrow metallic wire will support some very interesting plasmon modes. And in fact, you can put together a very simple theory. You can also do a very complicated theory, by the way. It's not so difficult to do it, but there is a simple, intuitive picture that you can use for understanding the modes of a wire. So here's a metal wire sitting in some dielectric, and of course we know that a metal supports surface plasmons. So if the wire is, not incredibly thin, like it's more than maybe 20, 30, 40 nanometers thick, you can view the mode as being formed from a surface plasmon that spirals around the wire. Okay, there's a surface plasmon mode that goes around the wire, and then one can use the fact that the wave vector component around the azimuthal wave vector component around the circumference of the wire has to add up to 2 pi, multiplied by the circumference has to add up to a multiple of 2 pi. And with that condition, you can work out the propagation constant of the mode of the metallic wire. So the refractive index of the mode would then be take this form, where this is related to the propagation of the surface plasmon mode. This is epsilon of the dielectric material outside. This is epsilon of the metal, and minus this is the mode order. The order of the mode. This expression is valid for n greater than 1. and this is the vacuum wave vector and the radius of the wire. So it's quite a simple expression. It turns out to be quite nice. So you can get different orders of modes. So there's actually m equals 0, m equals 1, m equals 2, and so on, that are guided on the wire. So we've done various different experiments on this. So we have a technique where we can selectively fill an individual hole in the fiber structure. In this particular case, it's a core that is rectangular in shape with two small holes in it, and we selectively filled one of the holes in the core. It's a similar structure, slightly different dimensions, and again we've filled an individual hole with gold in this case. And the diameter of the wire is 900 nanometers here and 600 nanometers in this case. And we do this by pumping in molten metal. So we have a system, high pressure system, where we melt the gold and we pump it into the holes. But that's done in a very simple, the concept is simple, but the technology is a little tricky. So the idea here was that we couple light into the glass core and see what happens as a function of wavelength. The experiment, well, here's the length of fiber, and we're controlling polarization. We have a supercontinuum source, broadband light coming in, and we just monitor with a spectrum analyzer. And here are some of the results. This is the transmission as a function of wavelength. And you can see we get a sequence of dips. And the dips correspond to the wavelengths where the light guided in the glass core becomes phase matched to one of the modes of the wire. So there's the m equals 4, m equals 3, m equals 2 mode for each of these dips. And you can do some theory on this and show that it's more or less correct. What I want to show you is how the light looks at the end face of the fiber at two different wavelengths. So let's first of all choose a wavelength more or less in the green, point A, and at this point you're far away from any of these dips. So you wouldn't expect any plasmon resonance, and that's in fact what we see. What you see here is a scanning electron micrograph of the structure, and superimposed on it the optical picture that we saw. And you can see the light is strongly concentrated in the glass, and the wire, which is over here, you can hardly see it. If, however, we shift to the point B, which is deep in the dip of one of these plasmon resonances, you can see the light has now coupled from the core onto the wire itself. So here you're actually seeing light which is guided by a plasmon mode on the wire. So, I mean, there are applications for this. You can maybe imagine some filters you could make with this. Polarizers, there are various different applications. You can also use these very fine wires as electrodes, for example, for making ion traps. I mean, if you have 4 of these wires, you can put an electric field across it, electric field distribution to create what's known as a pole trap, and trap ions in a hollow core. So I think some very exciting directions for these wires, moving in various directions. I mean, applications to telecoms devices, but also applications to Bose-Einstein condensates and optical lattices and all sorts of wonderful physics that one could do. We've also managed to push in to the holes, push semiconductors into the holes, and we've, for example, we've taken germanium and we've been able to pump germanium into holes small as 600 nanometers. And here's a 1.7 micron germanium wire. We're working with silicon germanium. And we've recently also managed to make silicon work. That's somewhat more difficult because silicon has a much higher melting temperature. But surprisingly, I mean, there are many applications you could imagine, making detectors perhaps with the germanium, modulators and so on. But just in terms of how good this material is, how crystalline it is, it's quite remarkable. The resistivity of these germanium wires is very close to that of crystalline germanium. It's only a little bit higher, 49 compared to 47 ohm meters. So the material looks reasonably crystalline, and we also did a micro-Raman study. This is a system where you focus laser light and you pick up the micro-Raman signal from the wire itself. And from this measurement, we discovered to our surprise that the germanium is almost crystalline. The resonant frequency of the Raman signal, frequency is only slightly lower than it should be, and there's no evidence of amorphous materials. We usually have a nasty kind of plateau on the left-hand side here, but there's no evidence of that. So it seems as if we're getting almost pure crystalline germanium, which does suggest that maybe you could make a semiconductor device, or you could, who knows where this will go. And you can also look at the optical transmission if you want, different polarization states, and once again one gets peaks, although of course these are not surface plasmons, these are guided modes of a dielectric strand essentially, which has, for germanium, admittedly the attenuation of germanium is quite high, but basically it's a dielectric, and once again one can get certain wavelengths, phase matching, and this is the kind of picture one sees. I don't want to talk about this in too much detail. If you're interested, you can look at the reference. There has, of course, been other work on this. There's some nice work from a group in Southampton in England where they've been using a high-pressure chemical vapor deposition approach to producing germanium and silicon in the fibers with quite a bit of success. So this is an alternative way of doing this. It's not clear to me yet which of these processes will be the most